Thank you all for joining another lecture for Introduction to Computer Graphics. Today's topic is a huge topic, is a very big topic, very, very important topic in computer graphics, especially in rendering, but also in other parts of graphics as well. Very, very important topic. But I would like to go over this topic, which is sampling. I would like to go over this topic in the context of rendering because it really is one of the fundamental things in rendering. That's why I'm going to talk about it in the context of rendering. So I'm going to actually start with rendering, start with where we left off, right, in rendering. So we were here. We were doing ray tracing, right? So this image is the iconic image of ray tracing. This image was first shown in SIGGRAPH 1979. See that? 1979. When this image was shown, minds were blown. People couldn't believe what they saw. This was, whoa, amazing. How can a computer generate something like this? Okay, I know, I see not all of you are really appreciating the value of this, right? So let me give you the context, all right? Let me give you the context. I'm talking about 1979 here, okay? So when you think about, for example, the PC of 1979 is this thing had just came out, the Atari 800, Model 800. This thing has a whopping extensible memory. You could extend it all the way up to 48 kilobytes. Yeah, you could have 48 kilobytes of memory. Can you believe that? Sorry, if this doesn't mean much to you, like what does that even mean? Like, so let me give you a context. If you're watching this video with full resolution, with 1080p, it's every frame of that in RGB, each channel being about exactly 8 bits. This would be about, one frame would be about 6 million bytes or something like that. So you'll need something like 128 of such computers just to store one frame of this video. All right, so I'm talking about times like this. All right, so like video games of the time, for example, this you know this guy, Pac-Man? It came out at 1980. It hadn't just come out yet, right? And people were not playing this on their computers or mobile phones or anything. They were playing this game on devices like this, right? So, I mean, that was the time. All right, so you're not impressed by this. Let me tell you. 2 years before, 1977, Star Wars used visual effects, computer-generated visual effects. And this is the computer-generated visual effects used in Star Wars movie. All right, so that's the first Star Wars movie. Pretty much everything else you've seen in that movie were all sorts of, actual physical stuff. All camera effects, nothing computer-generated. This was the scene that was computer-generated. All right, so this was the state of the art in computer-generated images in 1977. Right, so when people saw this, minds were blown because you see all these reflections and refractions. It was amazing. All right, so but today, when we think about this, when we think about this type of ray tracing, we call this Whitted style ray tracing. Why Whitted style ray tracing? Well, here's why. Because Turner Whitted is the first person who presented this. But then, not much later, researchers came up with a better way of using ray tracing and to be able to generate more realistic effects than just reflections and refractions. And they managed to produce something like this. This is Cooke style ray tracing, as we call it. Can you guess when that was generated? When this image was first presented? It's sort of hidden in the image. Hidden in the image. It says, you see, 1984. Yeah, 1984. That's right. So this was 1984 distributed ray tracing by Robert Cooke. This sort of opened up the whole possibilities of ray tracing. If you look at this image, even in today's standards, this is a fairly impressive image, right? I mean, it has a lot of very complex components here. There's shadows that are sort of soft. There are imperfect reflections here. and there's obviously motion blur, like all that stuff they could generate using a new type of ray tracing that was called distributed ray tracing. And after that, there came the rendering equation, a very fundamental work in rendering that sort of explained what we have been doing with rendering, and that also included a form of ray tracing to compute realistic images. It came up with a very fundamental algorithm for generating realistic computer images. It's called path tracing. Very, very important algorithm that was described in this paper. Now, you'll look at this image, maybe you're not impressed too much. I mean, it's all a bunch of spheres and boxes. Yeah, I mean, this is not a very impressive scene. But the algorithm itself, this path tracing algorithm, is still the algorithm we use in computer graphics for generating all sorts of super highly realistic imagery. For example, path tracing. Just examples from two relatively recent movies, right? Images rendered using that algorithm, that path tracing algorithm. Now, there are all sorts of other more complicated algorithms came out in the meantime, but path tracing is still a fundamental technique that we use. Of course, it got tweaked a little bit over the years, it got improved in many ways, but that is the fundamental algorithm that we use for rendering and generating super highly realistic imagery. And that is the topic of today. How do we start with this simple ray tracing of this Whitted style ray tracing that we talked about in our previous lectures and go to something like path tracing so that we can use that approach to generate super realistic images in computer graphics? That's the topic of today, right? And that is going to be hinged on sampling. But before we get there, I would like to talk about what it is that is actually happening in here. Now, when this work came out in 1979, we didn't have the rendering equation, right? So people didn't really explain this in the context of rendering equation. But I would like to actually step back and talk about this in the context of rendering equation, because rendering equation is something that exists today and we understand it, and we talked about this in our previous lectures. So I would like to put this in the context of rendering equation, right? So this is the rendering equation. If you all remember, it's an integral over a hemisphere placed over the point that we're shading, this point that we're shading. So it's over this hemisphere, we're looking at light coming from all directions, multiplied by the geometry term, multiplied by the surface BRDF, and this whole integral, basically summing all the reflected light along this direction, we get the reflected light, total reflected light towards the camera, and that's what the rendering equation describes. All right, we talked about this extensively, so I presume you have a decent understanding of what this equation does. Now, when it comes to computing this, however, we need to do things a little bit differently. So this light that comes to this point, from all directions, that actually includes two types of light. There is light that is coming directly from some light sources that are emitting light. But there's also light that is coming from other objects in the scene, light that is reflected light. And this concept is very, very important, and this is the fundamental thing, that when I talk about realistic lighting, this is what I'm talking about, just computing this integral properly, right? Yeah, this one integral explains what's going on and what needs to be computed very well, but when it comes to actually computing it in any algorithm, we typically do a little bit of a separation here. This incoming light term over here, we typically use different techniques for computing light that is directly coming from the light sources versus light that is reflected off of other surfaces. So the way with which we compute this incoming light for these two different types of incoming light is different, because you've already implemented this light coming directly from the light sources, right? We've implemented blend shading, and with blend shading we had a light source in our scene, and that light we're given a light direction. So we've been doing that. We've been handling light directly coming from light sources. We call that direct illumination. But the light coming from other objects in the scene, That's not something that we've implemented. So that's the bit that is important. That's where, if you can do this part properly, which is a lot harder than just computing direct elimination. If you can get this indirect elimination right, then we can generate super realistic images. Right? So what we typically do when it comes to computing this integral is that we're going to split this light term into two pieces. There's one term is going to have this direct elimination, that is light directly coming from the light sources. And the other term is going to be this indirect elimination, light coming indirectly from light sources. So basically what I did here is that I took the incoming light term and I split it into a sum of direct light and indirect light, and then I separate the integral into two integrals. It's just the same integral, just two copies of the same integral, right? So this part covers the direct elimination component. This is the part that we've been using. And this part just covers the indirect light, indirect elimination coming from all the other objects. This is the part that's difficult to compute. This is the part that's easy. Because, for example, if you have just a bunch of point light sources in our scene, or just directional light sources, this integral turns into a very simple thing, just turns into a simple sum. Right? We talked about this. If I have a number of light sources in my scene, I just add the contributions from all of these light sources and I'm done. So this integral is simplified fairly easily by just looking at a few light sources I have in my scene. Right? So that part is simple. Now I'm left with this integral. This is hard. This is not easy. So here is what, in my understanding of Whitted style ray tracing, what Whitted style ray tracing does here. Now, here's the trick. With Whitted style ray tracing, I'm going to first assume that this BRDF term here is something like a Blinn/Phong formulation. Okay, actually it doesn't matter which one you pick, you'll end up exactly at the same place. So it's just a Blinn or Phong formulation. That is, I have a diffuse term and a specular term, right? That's the first simplification that I'm going to make here. And then I'm going to say, you know what, this diffuse term, I'm not going to have a diffuse term. Do you remember we talked about having surfaces with perfect reflections? So if I have a surface with perfect reflections, then it's not going to have a diffuse term. Now, I might have a diffuse term over here. I'm not modifying this BRDF. This BRDF is exactly what it is, right? I'm not touching that one. It's just about the indirect elimination component, just this one. So over here, I am going to say this diffuse term is just black. That means diffuse reflections don't happen for indirect elimination. That means that if it is black, that means that term is going to just disappear, right? It's gone. Now, over here, what I'm going to do is that I'm going to assume that I'm going to have a perfectly flat surface, perfect surface, right? If I have a perfectly flat surface, that means that surface is not going to have any roughness. It's going to be perfectly smooth. And if it is the case, this alpha parameter over here needs to be infinity, right? Because as I increase this alpha term, remember that, the shininess term, as I increase it all the way to infinity, the surface becomes smoother and smoother and smoother. If it is perfectly smooth, then it is going to be infinity, right? And if I set this to infinity, something funny happens. This term, this cosine phi term, becomes 0 unless cosine phi is 1. So there's only one value here that will make this term non-zero. That is, if this angle is 0. That means if the reflection is in the perfect reflection direction, if this incoming light is in the perfect reflection direction of our view direction, that's the only case where this term is going to be non-zero. So this equation, when I set alpha to infinity, turns into this, right? So if the incoming light is in the perfect reflection direction, then that's okay. It's non-zero, just ks over cosine theta. Otherwise, it's 0. So if you just put this equation up here inside here, what happens is that this integral sort of disappears, right? I'm looking at all possible directions, but only one of those directions will really count. That is, it's the perfect reflection direction. All other directions sort of disappear, so I get rid of this integral, right? Because they don't matter. And if I put this equation in there, now the reflection incoming direction is always the perfect reflection direction. So I get this, and these cosine terms cancel out each other, and I get this. Remember this? This is what we came up with last time. We were saying the specular coefficient times whatever the reflected illumination is. So you look at the reflection direction, compute the incoming light, and that multiplied by the specular term. That's what we said. So basically, we can think about this Whitted style ray tracing as like a simplification of the BRDF when you're computing this indirect illumination term. And we didn't say KS, we called it KR. But I was saying if KR is not given to you, you should use KS because that's what makes sense. And from this explanation, I'm hoping that you have some understanding of why it makes sense to use KS instead of KR, right? It's supposed to be the same material, right? It's supposed to be the same BRDF, except that we sort of simplified that BRDF quite a bit, right? So this is Whitted style ray tracing. And if we did this, in 1979, minds are blown. Today, not so much. Today, we actually want to go back and try to compute this integral properly. All right. So the rest of this lecture is going to be about how do we compute this integral properly? How do we compute this integral properly? And the answer to that is going to be sampling. We're going to be using sampling. All right. So, but when I talk about sampling, I would like to start with something a little bit simpler than this whole indirect illumination computation. I would like to start over here. So let's say that I have two triangles like this, and I'm trying to render an image from these two triangles. And I am going to render a very low resolution image, something like this. Like an 8x8 image. Not a very impressive image, and not a particularly good looking image. And probably the most distracting part of this image is that it's aliased, right? It has these jaggedy edges because this is a very low resolution image, right? So this is an aliased image that is, I have these what we call staircase artifacts, right? I have steps of the size of a pixel forming these diagonal edges. A much better image could be generated using the same resolution image if I just use some sort of anti-alias rendering. So this is the same resolution image. Maybe when pixels are this big, it doesn't look that impressive. But if you look at it from a distance, this one is going to look jaggedy and this one is going to look pretty smooth and nice, right? So this is the kind of image that we want to generate, right? And here, the reason why we have these sort of soft-looking edges here is that because we picked the color based on what percentage of a pixel each triangle here was covering. Right? So that's what we're going to look at here. Let's pick one of these pixels here. I'm going to pick this pixel this pixel over here, and I'm going to expose it. Right? Just take a look at this pixel. I'm going to expose it a little bit. All right, so we're looking at that pixel. Now, in this pixel, as you can see, a part of it is covered by one of our triangles. The rest of it is our background color, right? But I need to pick a single color to represent this because I have one color per pixel, right? So a representative color for that pixel would be something like this. Overall, representative color for that pixel, right? So the whole point is, how do we compute this? How are we going to compute this? Let's say that I have this magical function f. I call it function f. I could call it something else. I'm just calling it f. F of x is a position. So given any position, this function f will tell me the color at that position. It's a continuous function. It's defined over this pixel. So this f of x at this point up here is going to give me the background color that is white. And the same function over there at that position is going to give me the color of the triangle that is blue. All right? So if I want to know the perfect color for this pixel, what do I need to do? I'm saying the definition of perfect in this case is that I would like to color this pixel such that color of the triangle is going to contribute to the color of the pixel based on the percentage of the pixel that is covered by the triangle. Right? So what I'm trying to say mathematically is that if I take an integral of this function over this pixel area, the result of this integral is going to give me the color of this pixel. Okay? So, yeah, that's what sort of integral means. But here's the problem. I said I have this magical function f, but I don't actually have a very good and precise definition of f always. I'm doing some rendering, I'm getting one triangle at a time and so forth. So computing this continuous integral without having this function is kind of hard. Even if we have this function, that can be sort of challenging, because this could be a very complex function, right? And mathematically computing this integral can be very, very difficult. And in a lot of problems that we're dealing with in computer graphics, we're going to have an integral like this, and computing this function, computing this integral analytically can be very, very, very difficult, sometimes flat out impossible. So what do we do? What can we do to approximate the result of this integral if we can't compute it? So we're going to do this numerically. We're going to numerically approximate it. And the way that we're going to do this numerically is we're going to do sampling. That's why this title stays here all this time. We're going to do sampling. So we're going to convert this continuous integral into a discrete sum. Discrete sum of a large number of points. Let's call it n is the number of points. We're going to take a number of samples, and those number of samples are going to, the average of those number of samples is going to approximate the result of this integral. All right, so I just picked a bunch of points here, and this should be fairly intuitive, right? So I can compute the value of f, value of this function at any point in space. My problem was just computing that integral. So I can compute the value of f here for any sample point, and if I just count the samples that correspond to the triangle and count the samples that correspond to the background, using the average of these colors, I can come up with the expected color for this pixel, right? So as you can see, as n goes to infinity, as I increase my number of samples, I'm going to get more and more accurate approximation of what the color is supposed to be. So this is the concept of sampling. I take a continuous integral and I convert it into a sum. All right, very, very simple concept. I convert it into a sum by taking a bunch of finite number of samples. Of course, the number defines here how much computation you're going to do. It will also determine how accurate the final result is going to be. So this is how we're going to solve this problem. But actually, this nice sampling pattern, this grid-based nice sampling pattern, it may look good at first glance if you just don't think about it too much, but this is actually a terrible idea. And let me tell you why. Now, if I have an edge like this and a horizontal edge like this, and when you're rendering images, horizontal edges like this actually happen quite often. This is not an improbable case. These kind of things actually happen quite often. Now, as this edge, as like my triangle that has this edge, as this triangle moves up, for example, it's going to cover more and more of this pixel, right? So here's what happens as I move this edge up. Yeah, it is not an edge case. So as this edge moves up, the triangle covered none of the samples. All of a sudden, it's now covering 8 samples. So the color turned from white to sort of this blue. As it moves a little bit, all of a sudden, it's covering 8 more samples. It turned into this one. As it moves up, 8 more samples like this, and then 8 more samples all of a sudden like this. You see where I'm going with this? So at some discrete positions in space, all of a sudden the pixel color changes from this to this, right? Again, moves up and this, moves up and finally covers everything and this. So that's a little bit of a problem because by doing this, as my triangle is moving up, I only got to 9 different shades of this blue, which is unfortunate because I have here, in this case, I have 64 samples, but I'm only able to generate 9 different colors, which is not very good. I mean, if I'm using 64 samples, I should be able to get 65 different shades of this blue, ideally. So, but of course, ideally, I would like to get something continuous, which we're not getting, but at least I should be able to get 65 different values, not just 9, right? So this sort of very regular patterns are pretty bad because of that. Now, we can actually fix this fairly easily. I can take this sampling pattern and I rotate it just a little bit. You see what's happening now? Now when this edge moves up, it's moving up. Now I'm hitting these samples one by one, so I am getting 65 different shades of blue. Perfect, right? It's great, it's wonderful. I can possibly do anything better, right? This is not going to have any problems, right? Unless my edge is tilted just a little bit. So if my edge is aligned with my sampling orientation, this is not going to do well. Okay, so rotating it didn't really solve all of my problems. What can I do? Well, ideally, what I would like is that I really don't want to have any recognizable pattern here, right? Because if I have a recognizable pattern like this, I'm going to have some edge direction where this pattern is going to fall apart. So this brings us to a very common technique that's used in computer graphics for sampling. That is sampling using randomly positioned points in space. So random sampling, otherwise known as Monte Carlo sampling. It's a very, very fundamental concept. And this is the concept that is used for solving all sorts of sampling problems. Now, a big topic which I'm not planning to get into here is how you pick this random pattern. Not all random patterns are generated equally. Some random patterns are going to give us relatively accurate estimations when you do this. Some random patterns are going to be more prone to inaccuracies using the same number of samples. And how we generate this pattern distribution so that you get on average a better estimation of this perfect pixel color is actually a big topic which I am not planning to get into. All right, but I want you to understand at least the complexity here that there's a whole bunch of work that's done in computer graphics and still continues about how to generate sampling patterns like this so that we get a relatively accurate estimation of the integral on average. I'm saying on average, that is important because whatever sampling pattern you come up with, there's going to be one case where it's going to be inaccurate. But on average, you would like it to be as accurate as possible. And by picking that sampling pattern carefully, you can actually improve your odds. And that's an important topic, very, very big topic, and I'm skipping that just by acknowledging its presence here. All right, but the concept is nonetheless the same. It's Monte Carlo sampling. We're going to somehow randomly generate a bunch of samples, and we're going to estimate an integral by averaging a bunch of random samples. All right, now let's get back to where we were. Our goal was this, right? Our goal was trying to compute this random equation properly. So what we're going to do to be able to compute this part of the integral more properly is that we're going to replace this integral, we're going to replace this really complicated, impossible to solve integral with Monte Carlo sampling. And that brings us to Monte Carlo ray tracing. So this was called distributed ray tracing. People came up with other names as well. Monte Carlo ray tracing is the name that I'm using here now. When you say Monte Carlo ray tracing, people will understand what you're talking about. So this is the concept, right? So here's how it works in this context. Now, my point is figuring out ways to compute this incoming light for any given direction, right? So what we're going to do is that I'm trying to shade this point in space. What I'm going to do is that I'm going to pick n different randomly generated directions here. Let's say this is one, here's another one, here's another one, here's another one. I'm going to just pick randomly generated directions, and I'm going to estimate this integral by using the average of these randomly generated directions. So that's the whole idea. Correction here. I think there's a missing pi term here. So this is not the exact term. Don't think about this as the exact term when you convert that integral, because the area of the hemisphere should also be factored in, which I did not in this equation. But I just want to mention that this is a representative equation than the exact equation that you would use for correctly computing this integral. So, and just like how important it is to pick samples distributed over a pixel, it is very, very important how you randomly generate these random directions. You don't necessarily want to generate them completely randomly. You probably want to factor in what this VRDF looks like. That's also another big topic in computer graphics. How do you generate these random samples so that on average you get more and more accurate estimation of this integral over here? That's again a big topic that I'm not going to go into, but I would like you to sort of appreciate this complexity that exists here. You can solve this integral by completely randomly generating these directions. That would be fine. It's just that your estimation is not going to be very accurate. You're going to need a lot of samples. But if you have a relatively better way of generating these random directions, you can have, on average, a better estimation of this integral using relatively fewer number of samples, right? So that's another big topic, another important thing that made realistic rendering possible today. People looked into this problem quite a bit. All right, so what happens with Monte Carlo ray tracing when I do something like this? Now with with Willett style ray tracing, I could do these perfect reflections, right? With Monte Carlo ray tracing, I can actually compute imperfect reflections like this. So in this case, the surface is not perfectly smooth, so my reflections, my visible reflections, can come from a whole bunch of different directions, and this is sort of estimating this integral for different directions using Monte Carlo sampling. Well, okay, to be honest, this is not an image that's generated using Monte Carlo sampling. It's just a representative image, so don't pay too much attention to this. I'm just trying to tell you that we can do stuff like this. But this is an image generated using Monte Carlo ray tracing, or distributed ray tracing, that was called at the time, or Cook-style ray tracing. Right? Now, what can we do with this? We can do a whole bunch of very interesting things besides the things that you see here. For example, if you don't include this incoming light from other objects and just use the Willett style ray tracing, you get an image that looks like this. This is an image generated using Willett style ray tracing. We have reflections and refractions, yeah, but we don't have any other form of indirect illumination coming in. Right? It's just the perfect reflections and perfect refractions. That's about it. So this is an image that looks very much like CG. Right? You look at it, yeah, this is a CG image. This is a CG feel. And one thing we can do, for example, we can maybe fix these shadows a little bit. You see these shadows, they're very, very sharp. They have very sharp edges. But in reality, we don't really get shadows like this. In reality, shadow edges are sort of smooth, and that smoothness sort of depends on the distance of the shadow casting object to the shadow receiving object. But the reason why we have soft looking shadow edges in reality is that in reality we don't have point lights. We have lights that look very much like this one up here. we have light sources that have some size, right? The point light cannot exist in reality because anything in reality has a size. Any object in reality has a size. So only point lights would generate shadows so crisp like this. Light sources that have some size will not going to create crisp shadows like this. They will create shadows that look more like this, right? So they will have softer edges. And this is really a function of the light source here and how big the light source here is here. So how do we compute this using Monte Carlo ray tracing? Well, if I have a point light, I'm sending a shadow ray to the point light and I'm sampling that. But how do I send a soft shadow ray to an area light? Like, what do? The answer is simple. We do Monte Carlo ray tracing. We pick a bunch of samples on the light source and we randomly sample that. So that's going to give us an approximation of the illumination coming from this area light, right? So we will do a Monte Carlo estimation there. That's going to be one way of computing this soft shadows or shadows from area lights. This is the standard technique used today for computing most soft shadows. And this is probably the only method we have for accurately computing the soft shadows coming in area light sources. Well, this is not the only way though. There are other approximate techniques for sort of softening the shadow edges and sort of approximating what the softness would look like. There are other techniques like that in computer graphics, but this is the way of properly computing these soft shadow edges. And that's going to be Monte Carlo ray tracing. Okay, I did that. All right, my shadows are soft and whatnot, but this still doesn't look very impressive, right? It's still, meh. I mean, it's nice and all, but meh. Still looks very CG. The real part, the important part that would make an image like this much more realistic is handling the rest of indirect illumination. So this was making the direct illumination nicer by using Monte Carlo sampling for direct illumination. Now, if we do Monte Carlo sampling for indirect illumination, we can get a much better looking image. Now, what's missing here for shading these pixels is light that is reflected off of other objects. Light that is reflected, for example, off of the walls of that funny looking room. This is actually what's called a Cornell box. If we include this, if we include light that is reflected off all the walls, then we would get something more like, you ready? This. Now, this is including a bunch of effects. One of them is light that is bouncing around in the scene, so light that's generated from this light source, but then hits one of the walls and bounces off and hits another wall, and then another wall, maybe one of the walls, and then bounces again, and hits something else, and then finally we see it in our camera. This is an image that actually compute this really massive integral of lights bouncing around in the scene. And as you can imagine, this is a very complex, very, very computationally expensive problem to solve. But if you do this, and if you do this right, and if you have a nicely modeled scene, then things start looking super realistic. And this is where the secret of computer graphics realism is hidden. So this is the difference between generating an image that looks like this, that totally CG, versus something that could be real. I mean, I don't know if you ever actually built a room that looks like this, but still, you know, if you build something like this could be a photograph. And if you have a more complicated model in your scene, like if you have a more complicated scene, all of a sudden things start looking a lot more realistic here. And there are other effects here. For example, over here, let me see my finger. Can you see my finger? It's over there. So this is what we call caustics. That is light that's passing through that sphere. Effects like this are possible to compute using Monte Carlo ray tracing. More specifically though, this image was generated using the algorithm that we call path tracing. Remember path tracing? I mentioned the path tracing when I showed you this image, Kajia's the rendering equation. So this is the algorithm that is used today for generating all sorts of realistic images. Path tracing can be thought about as a special case of Monte Carlo ray tracing. So this is the Monte Carlo ray tracing setup, right? Indirect elimination is approximated as a sum of finite number of samples. For path tracing, what you need to do is very, very simple. But before I get there, I would like you to appreciate the complexity of what's going on here first. Now, I would like to know at this point the amount of indirect light coming from all directions, right? So what I did is I picked a bunch of samples and I figured out how much light is coming from all of these directions. Here's the thing. How am I going to find this? Pick one of these directions. How am I going to find the light coming from that direction? I'm going to do what we said we're going to do for regular reflections. I'm going to trace a ray and find out where that ray hits, what that ray hits. And then I'm going to shade that point and figure out the light coming from that point. Here's the thing. At that point up there, I'm going to do another shading. Now, am I going to include indirect illumination at that point? If I am going to include indirect illumination at that point, then I am going to generate a whole bunch of random directions from that point, right? And for each one of those, I'm going to trace another ray. Oh, am I going to include indirect illumination there? Yeah, that means I'm going to... So what happens here is that, now I started with one ray from my camera. One ray from my camera. A ray hit here. Let's say I'm going to pick a small number n here. Very, very small number. I'm going to say 10. 10 is probably not a big number, right? I want to know all the light coming from all possible directions. 10 is a very small number. So I picked 10 different directions. For each one of those, they will go and hit something. From each one of those, let's say I'm picking another 10 directions. For each one, so what happened here? I started with one ray turned into 10 rays, and 10 rays turned into 100 rays. For each one of those, I'm finding another hit point, and there I'm also computing indirect illumination. Those 100 rays became 1,000 rays. From there we get 10,000 rays. So as many bounces as I'm adding on top of this, I'm getting exponentially more and more rays. And at some point, this becomes impossible to compute, right? So with this sort of distributed ray tracing, we can handle very few number of bounces. With path tracing, Kajia's brilliant conclusion for computing this integral was that how about I pick n equal to 1? What? Well, okay. Computationally, if n is 1, I start with one ray, I'm going to get one indirect illumination ray, and then I'm going to get another one. So it's not exploding anymore, right? So I don't have this exponential growth. Okay, I mean, computationally it's manageable, but 1? Come on. I mean, I say, I am going to approximate light coming from all possible directions. I say, let me look at that direction, and I'm done. I mean, how is that approximating anything, right? I mean, when you don't think about it much, this seems like a very dumb idea. It's just, how can you possibly approximate it by just looking at one random sample? But here's the brilliance, really. We're not ending there. This is going to be a bit more complicated. But by picking one, I ended up with something like this, and I'm going to show you how something super simple like this can actually give us the result that we want. So let's take a look at how path tracing works. Here's my camera. I'm going to generate an image looking at a scene, and I'm going to pick a pixel. Wow, that's a giant pixel. Yeah, okay, this is a giant pixel on this. This was a very low resolution monitor, okay? So pixels look like this. I have to pick a giant pixel, otherwise I can't show you what's going on in a pixel, right? All right, so this is one pixel. This is not an area of an image. This is just one pixel. I'm going to have just one color value here for this entire rectangle. Right? One pixel. Now, I pick a sample on that pixel, and I'm going to generate a ray, and I'm going to traverse that ray. I'm going to find where that ray hits. Now, I'm going to do shading and all that, but I'm also going to do approximate the indirect illumination. So for indirect illumination, I'm doing path tracing, so I just pick one random direction. There it is. Randomly, I pick that direction, and whatever I find there is going to be my indirect illumination estimation. Okay? Let's go along with it. So I traced that ray, and I found another point in the scene. All right, I'm shading that point. While shading that point, I'm going to approximate indirect illumination there as well. So again, I'm going to just pick another random direction. Right? Pick another random direction. I trace this. And there, I pick another random direction, and I trace that. So, like, eventually, what this whole thing is doing is it's generating a path for the lights. From the lights, there exists a path such that light bounces around like this and comes to the camera. So a path like this exists such that you get light to the camera. So by doing this, I've explored one possible light path from the light source, light coming all the way to the camera. Okay, to be accurate, I actually discovered multiple light paths, because if I'm doing shading at every point here, I'm explicitly looking at the light sources. So I'm looking at, I actually discovered many light paths, not just one. Right. But that's the idea, right? So we picked one sample here, and we discovered a bunch of paths, discovered a bunch of light paths for that correspond to that one sample. Okay? Now, this is not going to give me a very good estimation of indirect illumination. Big surprise, right? I just picked one sample for indirect illumination. It's not going to give me a good estimation. It's not going to give me a good estimation. So what do I do? What do I do? So this was my one sample. What I'm going to do is I'm just going to pick another sample, starting from my pixel. I just pick another sample from my pixel. And I trace that, find another point, and again I pick another random direction over there, and I trace that, find, explore all these paths and find all these paths. And when I'm done, I start with another random point, another random sample from my pixel. That corresponds to another point, and I explore that, another random sample, that corresponds to another point, and another random sample, that corresponds to another point. So, you see what I'm getting at here? So yeah, even though these are all different samples starting from different points on this pixel, they sort of go to a sort of similar areas in my scene. So if you look at collectively all of these rays, all of these randomly generated rays collectively, it's as if I am sampling a bunch of directions over a hemisphere for an area. Not for a single point, but for an area. So that's the whole idea, that I don't have to accurately compute this integral for every one of my pixel samples here. Each one of my pixel samples, each one of them will be very inaccurate. But collectively, when I have enough number of pixel samples, eventually I will be exploring this hemisphere well enough that I'm going to have a better and better estimation of the illumination here. That's the idea of path tracing. Right? And path tracing is a very versatile algorithm. We have other more complicated versions of path tracing and more complicated algorithms that exist in computer graphics. But of all of them, path tracing is still a very commonly used algorithm because it pretty much works in all cases. If you wait long enough, it's going to converge to the correct results. And in comparison, this is actually a relatively easier algorithm to implement correctly. So let me show you an example of what happens. Of course, I need to have a lot of samples from this pixel. Right? I need to have a lot of samples from this pixel. What happens if I don't have enough samples? What if it happens if I use very few samples? That means my estimation for this pixel is going to be inaccurate. So that means the image that I'm generating is going to be very noisy. Yeah, noise. Here's an example showing how an image converges as I increase the samples per pixel. So SPP means samples per pixel. So it's starting with a very small number of samples per pixel, which is, I believe, 100. Yeah, it's super noisy. To be able to get a good estimation of indirect elimination, I need to look at a very, very large number of samples, right? And eventually, as I add more and more samples, I get an image that is converging to what it's supposed to be. With path tracing, one problem is that this convergence becomes, at first it's pretty good, but convergence becomes, you see like the numbers are increasing sort of exponentially, but the noise is reducing sort of linearly. So I need to add exponentially more and more samples, reduce the noise the same amount. So you need to wait for a very, very long time to generate an image that doesn't look noisy. So what made path tracing very popular today is some advancements in a topic that's called denoising. It's an image space operation. So let's say that I generated an image like this using path tracing. I rendered, and this is the image that I got. I'm not sure if you can see in your monitors, but this is a fairly noisy image. Right? You see some black spots all over the place. It's a very, very noisy image. So with some denoising algorithms that looks at this image and also looks at the components that form that image, like the indirect illumination, direct shadows, and all that stuff. By combining this and then filtering them in different ways, we can get rid of this noise. After we render this image, we can actually apply some denoising filter and get something that looks like this. So we can go from here, and we're done with our rendering. We're not doing any more rendering. We take this image, and then we just process that image using some denoising algorithm, and we get something like this. Just estimates what the finally converged image would look like if we had enough time to wait for path tracing to finish. So this is a very, very important and relatively recent development in computer graphics that made path tracing very, very popular, because we no longer have to wait for path tracing to converge. We can just render enough to get a good enough estimation of what the scene is supposed to look like. I mean, when you look at this, you have a pretty good idea about what this will look like when it converges, right? So these denoising algorithms is sort of generating an estimation of what the converged image will look like. And we have pretty good denoising algorithms today. This is just one example of Intel's denoiser. Other companies have denoisers as well, denoising algorithms. They're quite a good collection of denoising algorithms that exist today. Still an active research topic. But yeah, we have very good algorithms for this, and we can generate images that look like they're totally converged. Right. There it is. So this is going to work out using what we call image space filters. And that is going to be image space filtering and all sorts of image space operations is going to be the topic of our next lecture. So next time we're going to talk about this. We're not going to talk about denoising specifically. We're going to talk about the whole image space operations in general, not in the specific context of denoising. Yeah, so I'm not going to go into the details. I'm not planning to go into the details of a specific denoising algorithm here. So I'm just going to end it here. I would like you to know that this exists, and this is the magic. This is the magic that makes path tracing work in practice, even when we have relatively few number of rays per pixel. Relatively few. Like, we don't have to go to millions to get an image that looks like this. In some cases, we can even produce images that look pretty decent using just a few samples per pixel. Yeah. So, that has been the topic. of this lecture. That's what I plan to talk about today. So I'll end it here. Thank you all for joining, and I'll see you all next time.